Swayam Prabha. Digital India. Educated India.
Before going to the mechanism of interaction between particles and turbulence, let's discuss first the modeling approaches in particle-laden turbulent flows. So, if you see the chronology, first we discussed the transport equations for single particles. Then the behavior of single particles when the carrier phase is prescribed. Then we considered the carrier phase equations along with the particles, such that this introduces the source terms in the mass, momentum, species and energy conservation equation for the carrier phase. Then we discussed turbulence. So, now we have to model particles in turbulent flow. So, where we have these two factors present. First one is presence of particles, then turbulence. So, how do we now model such case, which is the final real case, you see. So, again we have to revisit the particle equation of motion. So, to start with, we consider the particle momentum conservation equation, and which is the Maxi-Rayleigh model. We have already discussed this. So, here the force on the particle is basically summation of gravitational force, force due to the undisturbed flow, then steady state drag, which has two components, one is Stokes drag, one is the friction forces. Then we have virtual or apparent mass term, and then the history term. So, now if we have a turbulent flow, the question is, should this model be used, or what is the validity of the model? Can we use this model? Okay. And how far it will give accurate result, because this is the basic to start with. Okay. So, the answer to this question is that yes, it is valid, but under certain conditions only. So, what are the conditions? These are summarized here. So, the Maxi-Rayleigh model works well only if the following conditions are met. First one is the particle Reynolds number is much smaller than 1, because we have to ensure that the Stokes drag is valid if we have the linear drag law. Okay. Then the particle size must be smaller than the smallest length scale of the flow, that is the Kolmogorov scale. Now, why this is required? Because only in such case the flow around the particle can be assumed spatially uniform, as it was considered in this model. No need to resolve the local flow disturbance, and because the particle size is smaller than the smallest scale of turbulence, we do not have to resolve the local flow disturbance, for example, the wake effect. Then the other criterion is that we should have low particle volume fraction, such that there is no significant two-way coupling, or in other words, the fluid is not strongly affected by the particles. So, now why this is required? This is required because this ensures that the undisturbed fluid velocity can be adequately defined. Now, what is meant by undisturbed fluid velocity? So, if you see in this equation, what is u here? U is the flow velocity. So, you have a particle and there is a flow. Now, but where is u defined? At which location should we consider u? U is the free stream velocity. Okay. This is not the velocity within the boundary layer. Anyway, in this case, the assumption is that the Stokes number is very small, or the Reynolds number is very small. Okay. But we are outside this zone. We are in a zone where the fluid velocity is undisturbed by the particles. But now you imagine you have large number of particles around it. Okay, you may not have here the case that one particle is in the wake of the another particle. Even in that case, the local fluid velocity here is influenced by the presence of other particles. So that is why the definition of undisturbed fluid velocity becomes tricky here. So what is undisturbed fluid velocity as in the previous case? Because the fluid is itself influenced by the particles. Why? Because if the loading is high, or we are in a zone where we have two-way coupling, even if there is no particle-particle interaction, if we have two-way coupling, then we will have issue in defining the undisturbed fluid velocity. And then the Stokes number is much less than 1, or is of the order of 1. Okay. So now under these conditions, the Maxey-Rayleigh equation for particle momentum is valid. And under these conditions, the point particle approach is valid. So if you remember, we had discussed this modeling approach, that is point particle approach. So what is point particle approach is that the particles are considered as point. So we account for the force exerted by the particle, heat transfer by the particle, but we don't consider this to occupy some finite space. So this is a modeling approach. This is not reality. Okay. But to simplify the situation, we assume this. So if the particle size is much smaller than the Kolmogorov scale, then we have this point particle approach valid. And why this is advantageous? Because we don't have to resolve the flow field around particles. Now in this case, what happens? All these terms basically drop out because they are negligible. So we are left with basically the Stokes drag term and the gravitational term. So this is the advantage of the point particle approach, for which we can directly use the Maxey-Rayleigh model. But then the question is, what would happen if the particle size is of the order of Kolmogorov scale or even larger? And this can happen. Means why should in real world application particles would prefer to be below Kolmogorov scale? This is not realistic. So anything can happen. Now in such case, the particle turbulence interaction becomes far more complex and also interesting. Let's see why this is so. So first of all, in this case, the point particle assumption now breaks down. So this assumption is violated now. The flow field is no longer locally uniform over the particle volume as was assumed. So now we have to consider the faction correction. That is, if the flow field is not uniform, there is some non-uniformity, then the faction force accounts for that. And the particle now samples velocity gradient across its surface, which means that the fluid velocity at the particle center is no longer representative. So what is meant by fluid velocity at the particle center? So let's say you have a particle here which is moving with this velocity v. then the drag is given by 3 pi mu relative velocity times the particle size, we know this. And as I said, what is this u? This u is actually this undisturbed fluid velocity which is seen by the particle. What with reference to the particle, what is the fluid velocity that the particle sees? That is called the undisturbed fluid velocity seen by the particle. And now this is what is used in the drag term. Now, if we have the point particle assumption valid, that is the particle size is much smaller than the Kolmogorov scale, then in that case, we can define both these terms u and v at the particle center. Okay. But if we have this case, if the particle size is larger, then the question is what should be u, or u should be chosen at what location? Okay. So, this model basically there fails. So, how should we calculate drag in that case? You have to calculate the drag locally at every point, the stress at every point, or you can calculate the local drag and then integrate. So, that will give you the total drag. But for that, you need to resolve the flow around the particle. You need to resolve the boundary layer. Only in that case you can calculate the drag. While in the previous case we just used this model. So, that greatly simplified the situation. But now we do not have that scenario. Then, yeah, so as I said, the Stokes drag law is no longer valid, because the local shear and unsteadiness influence the force on the particle. In addition, we can have the wake effect or pressure distribution around the particle, which also needs to be solved. In addition, we may have the lift forces that we had discussed earlier significant, which requires more complex modeling. Then, if we have large particles, then turbulence modulation becomes stronger. So, in this case, the larger particles extract more energy from turbulence and dampen small scale fluctuations. So, this is also another effect by the particles. So, the large particles would try to dampen the small scale turbulent fluctuations. So, this is called particle induced dissipation, and in addition they can generate turbulence also through wakes. So, you see the situation is complex in the sense, in one hand they try to suppress the fluctuation, on the other hand they create more turbulence. Okay. So, in summary, if the particle size is smaller than the Kolmogorov scale, we can use point particle assumption. In that case, the linear Stokes drag, the Maxarelli model works well, all other forces can be neglected. If the particle's size is of the order of Kolmogorov scale, still we can use point particle model, but some finite size effect becomes important and we can incorporate that. So, imagine now considering other terms in the Maxarelli equations, not only the Stokes drag and gravity term, but still you can use the Maxarelli model. But once the particle size is larger than the Kolmogorov scale, then the particle strongly disturbs the flow. The wake turbulence modulation dominates and particle resolved approach becomes essential. So, if your particle size is large and you are using point particle assumption, the predictions will not be accurate. Okay. As we will see through some examples when we discuss turbulence modulation by particles. Okay. So, now we will go through these modeling approaches one or the method to solve the equations one by one. So, first one is direct numerical simulation. So, again we will revisit what we discussed earlier for single phase turbulent flows. So, the objective here is to see how do we account for the particle effect in these different numerical approaches. So, first one is direct numerical simulation. So, in this case, as we know, we solve the Navier-Stokes equations directly without modeling turbulence, which means that we resolve all spatial and temporal scales down to the Kolmogorov scale. Everything is resolved. Now, when we say we resolve everything, the question is it enough? So, if you have only single phase flow, then yes, if your grid size is smaller than the Kolmogorov scale, then you have resolved. But if you have particles, then is it correct to say that we resolve everything unless your grid size is less than the particle size itself? Are you getting it? So, the grid size can be smaller than the Kolmogorov scale, but still larger than the particle. Then in that case, you are not resolving the flow around the particles. So, in that case, it is not truly fully resolved flow, even if you are resolving the carrier phase. Okay. So, considering what we just discussed, that we have now broadly two categories. In one category you have particle size which is less than Kolmogorov scale, in the other one it is greater than or equal to Kolmogorov scale. So, accordingly we can have two different type of DNS. So, one is called fully resolved DNS at the particle scale. The other one is called flow resolved DNS with point particles. So, for these two cases or these two scenarios, we have different approaches. Now, what is fully resolved DNS at particle scale? That is, your grid size is smaller than the Kolmogorov scale, and in this case that means it is smaller than the particles also. So, this means that you are resolving the particle, the flow around particle. So, this is actually the ideal method because there is no modeling, no assumptions involved. This is the truth. So, here as I said, here we resolve the flow around each particle. How? Each particle surface is imposed as a boundary condition, and at every time step that boundary changes. So, this is the reason why this is computationally expensive. So, we can get the details which even cannot be captured, or it is very difficult to capture even in experiments. Okay. So, this is the ideal case, okay. And this is in a true sense fully resolved flow. Now, what happens if we have particle size less than the Kolmogorov scale? In this case, we can adopt the Eulerian-Lagrangian approach as we had discussed earlier. So, Eulerian is for carrier phase, that is you are fixed at a location. Lagrangian is for dispersed phase. And here we adopt the point particle assumption, or particles are treated as point forces, and we track and we do Lagrangian tracking of individual particles. But here we have to have the coupling terms or the source terms due to the particles in the governing equations for the carrier phase for two-way or four-way coupling scenarios. So, in this case we can consider also the two-way coupling, that is the particles influence the carrier phase, But as I said, if you have that situation, then every time you have to update the local flow field around a particle, because the flow field can get disturbed because of the presence of other particles. Okay. And this is again one of the reasons why the computational cost goes up, even when you have point particle assumption. Now, in this case, the fluid velocity is calculated at the particle position. So, as I just mentioned, in case of the point particle assumption, it is possible to calculate the, or to assume that the fluid velocity is defined at the particle position, and you calculate the Stokes drag term. Now, let us look at this more carefully. So, when we say fluid velocity at the particle position, what do we mean? So, again we consider, let us say there is a grid around the particles, and the grid size is smaller than the Kolmogorov scale, because this is DNS. So, now this is the drag term, where you have the carrier phase velocity, and this is the particle phase velocity. So, now you consider, let us say this is your grid and there is one particle here, and around the grid you have 4 fluid velocity vectors defined. I am showing this in 2D, you can extend this to 3D also. Now, the question is, how do you evaluate the drag? The drag involves the slip velocity u and u minus v. Now, v is this one, you are doing Lagrangian tracking. So, at any point of time, at any spatial location, you know the velocity of the particle. But how about the fluid velocity? What do you do with fluid velocity? So, in this case, you can interpolate the fluid velocity suitably to find the position. So, imagine you introduce some kind of interpolation function where you give these 4 vectors as input. Depending on where this particle is, you can accordingly calculate, you can do some interpolation, maybe weighted average of this depending on how close this particle to one fluid velocity vector. Okay. So, this is how the fluid velocity at the particle position is calculated, which is required to use the Stokes drag model. Okay. Now, how do we do source term modeling? What is source term modeling? This means that we have to now consider the effect of particles on the fluid phase. So, how do you account for that? So, we know that because of the presence of particles, we will have a source term here, which is basically the particle feedback term or momentum source term, which represents the force that the particle exerts on the fluid. But now the question is, how will you introduce this effect? So, you have the force defined at the particle position, right? But your fluid velocity are defined here. So, this means that you need to distribute this force to the nearby or neighborhood grid points, because even if this equation is valid at all points, this differential equation is valid at all points, but in reality when you do the numerical calculation, you actually calculate at the grids only, right? You cannot calculate at all points, okay, that is not possible. So, now this force needs to be, so this force is this one. So, this needs to be accounted for, but here you do not do any modeling, in the sense you directly compute the forces, drag, lift, etc., and apply exactly opposite force to the fluid at the corresponding grid cell. But for that purpose, you need to use some kind of interpolation to distribute the particle forces, as I said. This is nothing but a numerical way to distribute the particle force to nearby grid points. But there is a difference between this term that we see here and the source term that we had derived earlier. Can anyone guess why there is a difference? How we derived the source terms earlier without considering turbulence? It was by considering the volume averaging, if you remember. So we basically volume averaged all quantities, okay, and then we got the source terms. But in this case, we are not doing that. Okay, there is no volume averaging. There is only redistribution of particle force to different neighborhood points. Okay, and depending on how many particles, the number of particles you have within a grid. For example, in this grid, you have 5 particles. So you have to consider the effect due to all 5. So for each one, you redistribute the force, and go on doing that for all points within your grid. Okay. Okay. So as I have already mentioned, such approach, either the fully resolved is definitely more expensive compared to DNS with point particle. But in any case, the application of such kind of simulations are for fundamental studies on particle turbulence interaction. For example, to understand such effects like preferential concentration, turbulence modulation, we will see this at a later stage. And also for model development and validation. And this act as a benchmark data for LES and RANS models, especially the closures that we use for RANS and LES calculations. So the DNS can provide the data for validation. And this is extremely expensive. It is only feasible for low Reynolds number flow and when we have small number of particles, and it cannot handle realistic engineering or industrial flows. We know this. Okay, so let's move on to the next approach, that is Reynolds averaged Navier-Stokes based modeling. So in this case, we know that we solve time averaged equation. So this means if you solve the RANS equation, what you get is the mean flow field only. The turbulence effects are modeled using different models, as we have already discussed. So now there are few important concerns that are present in this type of modeling approach that we will discuss. Now here we have to keep in mind that the RANS based particle tracking is fundamentally built for particles smaller than Kolmogorov scales only. Okay. Usually we don't consider RANS modeling where we have large particles. When I say large or small, this is with respect to Kolmogorov scale. Now, why is this so? This is because this type of decomposition is valid only if the flow is uniform at the particle scale. What does this mean? Now, you imagine you have few large particles in the flow and each has some wake effect. Now, due to wake, some turbulence, let's say, is created. Now, for this kind of situation, it is not possible to do such decomposition because the flow field is not uniform. You cannot use this everywhere. Okay. So, by default, the RANS based modeling is suitable for small particles only. That is what we have to keep in mind. Although we can introduce some corrections if we have the particle size close to Kolmogorov scale. But beyond that, we should not use RANS based modeling, and we have to use particle resolved DNS or LES. So, RANS based modeling is mainly divided into two categories. If you remember, we had discussed this earlier. One is Eulerian Lagrangian, where the carrier phase is solved in an Eulerian reference frame, but the particle phase is Lagrangian frame. We have also Eulerian, where both particle and the fluid are treated as interpenetrating continuum. Okay. So, and these are known as two fluid models. Now, if we consider Eulerian Lagrangian itself, we have two different approaches: discrete particle method, discrete element. So, this should be discrete element method. Okay. Now, yes, so this is another very important point. So, as I said, in case of RANS, what we get is mean flow statistics only. Again, if we go back to the problem of let us say turbulent jet, and you introduce some particles, and you want to use RANS based modeling approach to solve this flow. So, first what, and let's assume for simplicity that you have one way coupling only, that is the particles are not affecting the carrier phase turbulence. So, what would you do? First you will solve this for the single phase flow, and then introduce particles, because particles anyway do not affect the carrier phase, and then you can track the particles and study how they are dispersed. So, that is the objective. But when you solve the RANS equation, what you get is basically the mean flow, or in other words, if you show, let us say, contour of the flow velocity, you will not see these corrugated shapes, you will see this. This is because it gives you the average flow field only. It does not have the turbulent fluctuations. Even if you have modeled the turbulent kinetic energy, let us say you are using K epsilon model, then you solve the equation for turbulent kinetic energy and dissipation rate, and from there you basically you get the eddy viscosity term. Okay. But still you do not have the instantaneous fluctuation data. So, now what will happen if we introduce particles to the solution from RANS model? Then the particles would respond to the mean flow only. So, you will not see any fluctuations in the particle trajectory, and also many effects such as the turbulent dispersion of particles, you will not see those. So, now how do we deal with it, which is incorrect? Means you cannot predict the true behavior of the particles. So, to deal with this scenario, dispersion models are used. Now, what are dispersion models? So, as I said, if we do not use the mean velocity, the particles would follow smooth streamlines. There is no turbulent dispersion, no spreading, which is unphysical. So, the actual equation is this. This is the momentum equation. But what you are doing now is this. Notice the difference. You can still calculate the particle trajectory, but you are using the mean velocity. So, application of this equation itself is not correct. It's wrong, because this is the original equation. Okay. Now you can argue, okay, why don't we average this equation itself? If we do time averaging of this equation, won't we get this term? What do you think? The answer is no, you won't get. Why not? Why? Because you see, you are considering the fluid in Eulerian reference frame. That is, you are at a fixed location, okay, and you are time averaging the fluid velocity to get this. But you are dealing with the particle in a Lagrangian reference frame. The particle is moving. You cannot treat that in this model. You cannot treat it from Eulerian reference frame. So, if a particle is moving in space and if you calculate time average, it does not make any sense. You cannot write, means mathematically you can write this, you can calculate this also, but it does not make sense because this is defined in Lagrangian sense while this is defined in Eulerian sense. So, time averaging this equation to get this does not make any sense at all. That is why what you can do, you can get the mean flow field, introduce here and calculate the particle trajectory. But this will also this won't work as well. Why? Because the particle will respond to the mean flow only, which is not physical. You can calculate, but it's not physical. So, to avoid this, the dispersion models are introduced, which basically artificially reconstruct the effective velocity fluctuations and their effect on the particle trajectory. Okay. So, now what are these dispersion models? One example is the random walk model. So, random walk model means we have this, we superpose, you calculate u dash some way and superpose at that instant of time. How it is done is, you know, basically from your RANS modeling, you know the turbulent kinetic energy, and by assuming isotropic turbulence, so you see you are introducing more and more assumptions. By assuming isotropic turbulence, you can say that the velocity fluctuation in all three directions are same, and that is equal to 2 by 3 k root over. Okay. So, this is basically your u dash. So, this represents standard deviation of the distribution. So, if you assume a Gaussian distribution, let us say this is u mean, and you know the standard deviation of so basically this is actually, let me write this as standard deviation, and this is the standard deviation of the velocity. So, and you assume again that the velocity fluctuations follow a Gaussian distribution, then it is possible to prescribe these velocity fluctuations. Okay. So, how you do is that you choose any one random value out of this distribution, okay, and then introduce that here, and then calculate the instantaneous velocity and use the instantaneous velocity here to calculate the particle trajectory, and you go on doing that. The fluctuations are generated every integral time scale. So, what is integral time scale? This corresponds to the basically the ED turnover time scale or time scale of large scale EDs, which you can calculate through this, and you regenerate these fluctuations after every integral time scale. So in simple what you are doing is that you actually calculate the mean, you have information about the standard deviation. Using that, assuming Gaussian distribution, you create one u dash and put that here to calculate the instantaneous velocity and then calculate the particle trajectory. So this is only one example which is known as random walk model, which is a popular model. Similarly, we have discrete random walk or ED lifetime model, continuous random walk, PDF based approaches. So there are different models here itself, okay, and they can be used as a compromise between accuracy and computational cost, okay. But after all these are models, okay. You are basically introducing some approach to calculate the particle behavior, but this does not represent reality. So this is the reason why comparison with experiments or validation is extremely important. Now we consider the source term modeling. So how do we do modeling for the source term in RANS based models? So the question here is, the RANS equations are time averaged, while the source terms are obtained by ensemble averaging the Navier-Stokes equation. Is it correct to simply add the source terms in RANS equations? So the point which I am trying to make here is that, how do you calculate the source term? So if you see here, yes, so this one. So how did we calculate this source term? So we considered the contributions from individual particles in a grid, okay, and using some approach you distribute and you add that force to your equation. But this happens at one instant of time. But when you do RANS based modeling, you don't have that luxury. There is nothing called an instant of time. You basically solve the mean flow. So now the question is, if I simply do this to the mean flow, will it make sense? I hope it is clear. So here we can add the source term, okay, and account based on the number of particles we have in a grid. But in case of RANS-based modeling, we have the mean flow, and these equations are written for the mean parameters. So is it possible to simply add one source term? And if we add, it should have the results from ensemble averaging. Ensemble averaging means you account for all particles in one grid and for all time instants. Okay, so how do we approach that? So time is up, so we'll continue this in the next class.